Hello, everyone. Yeah, I'm Hongtao, presenting on behalf of the Triton compiler team at Meta. So we have developed TLX, which is a low-level language extension to Triton, and it's designed to bring performance spike to higher level with minimal changes to code. So here's the outline today. What I'll be covering is I'll start with the motivation and why we built TLX and what gap is trying to fill. And then I'm going to give a high-level overview of TLX, followed by our core building blocks that push the performance forward. And then we'll do a kernel study for its performance for a realistic kernel. And then we'll wrap up with some takeaways. So yeah, Triton is so great, right? It provides exceptional productivity through tile-level abstraction and automatic thread mapping. And it's hardware agnostic. You write a Triton program once, it runs everywhere. And it already delivers very high performance on CUDA cores. But we still see it can go further, right? So especially on tensor cores. So many of our customers want to push forward their Triton performance to limit. And without switching to a completely different language. And they are looking for a tenable path to automate performance and predictable behavior across shapes and kernel variants in production. And they're also looking for a faster path to adopt new hardware features as the GPU evolves very quickly and without relying on the compiler to do everything. So that's why where TLX comes in. So TLX as a Triton low-level language extension, it extends Triton DXL with low-level hardware intrinsics. And this provides user a way to go deeper into the hardware and control what exactly behaves. And it exposes fine-grained control over hardware's features like memory hierarchy, synchronization, and tensor core pipelining. And this all the knobs that matter for peak performance. And it also has unnecessary complications like layout encoding. So it integrates into the Triton compiler seamlessly. And so user can always start with a regular Triton program and drops into TLX when they need that level of control. And this provides an incremental way to achieve performance while maintains Triton's composability and simulability. So let's look at how TLX helps performance for a particular example. So you are looking at a standard implementation of a dot compression kernel with Triton. So here we are doing 2 jams in a row. And with the second jam, you use the output of the first jam. So you typically have 2 loops in the kernel. And with the compiler automatic pipeliner, you got a very good performance for that. So the pipeliner will pipeline each loop perfectly in this way. So in this example, let's say we have 4 warps running this kernel, and we have 3 buffers for each input. And with pipelining, the tensor core can be busy all the time. So you already have a bubble there. The tensor core has continuous execution of the memory ops. And also for the memory load, it's also similar. And this is perfect for the first loop. And for the second loop, it's similar. But what we can see here, there's still a gap between the 2 pipelines because the loops are independent. The compiler cannot fuse them together, or it doesn't know how to do that right now. So, and this we see an opportunity here. We can push it further, and by getting this prefetching for the data of the second loop into the first loop. So in this way, the tensor core are fully busy. There will be no bubbles, and the load pipeline is also busy. And this is what we call continuous pipelining. In this case, it gives about 20% speed up. And let's see how TLX makes this possible. With TLX, user would have a very explicit control over shared memory buffers. But here, we are using local iLog intrinsics to manipulate shared memory allocation. And yeah, we allocate buffers for each input, and some inputs just share the same physical buffers because shared memory has a limited size. And yeah, once the allocation is done, we move forward to prefetch data for the first main loop. This is also known as the prologue of the main loop. But in the main loop, we also did a little bit prefetching for the future iterations. And note that the epilogue of the first main loop is peeled out and fused with the prologue of the second loop. So this forms a continuous pipelining, and the load operations there never stops. It keeps running, and the MMA operations there also never stops. So this fully take up the full tensor core and improving its utilization. And another key point here is the async operations. We call async load and async dot. This makes it possible to overlap the data movement and the tensor core operations. So yeah, so this is just an example showing how TLX can in general expose direct low-level control to users and for performance. And we'll see more advanced building block later you'll be interested in. So TLX initially targets NVIDIA GPU. It exposes operations that map directly to PTX intrinsics. Those include local memory accesses, async global memory operations, async tensor core operations, and also work specializations available through our async task interface. And under the hood, those TLX ops almost map one-on-one to TDGR ops. So we are introducing TDGR ops into TDIR, forming a mixed layer, and we are making sure this works throughout the rest of the computation pipeline. And in this way, TLX integrates fully into Triton. And yeah, so it gives very seamless integration with regular Triton kernels. So one detail you may wonder about is layout encoding. And TR users never need to manipulate layout encoding explicitly. This is all done by the compiler automatically. And how this works is, so regular Triton symbols, we treat it as registers. It has register semantics. And its encoding is influenced by the compiler and comes from existing processes like memory coalescing and MMA operation shape inference. But on top, we are introducing a buffer tensors, right? That's model, shared memory, or local memory. And the encoding for that is also handled automatically by the compiler. So the compiler will start with a placeholder layout. Let's say it's non-serial layout. And then it propagates it throughout the kernel. Depends on the consumers. It depends on the user requirement. And all of this done is in our newly introduced layout propagation path. So it's priority aware, it's fully transparent to users. Yeah, so as we already see, pipelining is very critical, building blocks for ultimate performance. And we are going to go over the rest of it. So there's further building blocks that's very critical to performance on both Hopper and Blackwell. The first of it is the warp specialization. And so, yeah, so TLX makes it available through our async task interface. So you can wrap your code region under async tasks, and then you can allocate a single task for each region, sub-region that you want to run in parallel. And the schematics here is like, we always start with a number of warps for trunk code. We call it main warps. And the main warps are going to execute the default region as well. And for any other tasks, we are going to fork additional warps to execute it. In this case, we have 5 warps in all. 4 warps running the main trunk code and the default region, and 1 additional warp runs the actual async task. And but when they converge, the trunk code is resume executing by the main warps. So yeah, people, we already talked about, like in the previous talks, warp specialization is very important. We covered it a lot. Now I'm going to go over it a little bit here. So warp specialization can also speed up program, makes continuous pipelining, but in a different way from software pipelining. So typically, you would have different warps executing different tasks separately. And on H100, we typically allocate 1 work group, which consists of 4 warps for loading data for everything. And 2 additional warps, parallel cooperative warps that running MMA operations. This is the example for Jam. So, and how it works is the producer warps that does load kicks off first, and it starts loading the tile for the first MMA consumer. When it finishes it, it signals that consumer to proceed, and then start loading data for the next consumer. And when the consumer finish consuming that data, it releases buffer back to the producer. So these are done through these lightweight barrier operations that NVIDIA GPU provides. And this is a very useful technique on Hopper, and on Blackwell you would do something similar, but you wouldn't have two explicit workgroups for MMA, but you still do follow this model. And this also works well for gem kernel, where the epilogue is big, is heavy, and you want to hide the latency of epilogue between the two consumers. So with TLX, what we do here is we will start allocating buffers and then barriers, right, for communication between work groups. And then we allocate one single task for the producer group that does load for every consumers. And then, since the two consumers runs exactly the same code, but on different portions of the data, we have a convenient feature called replicate. We use that to differentiate the two consumers, but the code is still shared between them. And on top of that, we can also enable ping pong. So ping pong is a technique that allows a dot consumer to fully take over the tensor core pipeline exclusively before handing it over to the other group. And in this way, the epilogue overlaps completely with the tensor core op from another group. And it's a little bit different from the cooperative op, where the store epilogue can compete with each other. So this makes a different overlapping, but it proves to be very useful for some cases. Like for gem kernels, especially when the epilogue is heavy and when the K loop is light, you will typically do this. And also for the flash attention kernel on both Hopper and Blackwell, you will do ping pong for the softmax part. And yeah, so ping pong can be implemented using the weight barrier or arrival barrier previously. We've seen that. But here, TLX is offering a slightly more efficient way, like to using name barrier to achieve that. But actually, the idea is pretty simple here. You basically, one consumer can issue a start operation only after its previous start has started. So these two groups literally ping pong the tensor core back and forth. They take turns. And yeah, with all those techniques, we have rewritten one of our commercial kernel. It's known as the two-symplectic attention kernel. It's also known as the triplet attention kernel, and with TLX, and this achieves almost double performance. And this kernel differs from a regular attention kernel, as in that it models more complex interaction between triplet of tokens instead of pairs. So it uses trilinear function to interact between one query and two sets of keys, and also two sets of values. So the original kernel is written in Triton, and it's purely rely on the compiler's automatic pipeliner for perf. The perf is good there, but we see a lot of room for improvement. So we redesigned this kernel in a work specialized way, such that we allocate one work group for all the data movement job, for loading data for all the consumers. And then we allocate two parallel cooperative consumers that handle all the mice here. And the mice is going to be the tensor core mice and the CUDA core mice, and also the exponential thing on the SFU unit. The goal here is to have the MAOP fully connected, continuous taking the tensor core pipeline and overlapping with any other, all of the rest of the operations. So we've been using the Proton provider to validate this idea. And as you can see here, the cooperative work specialization path is pretty good. It gives quite good performance, but we can still see a lot of tensor core bubbles here, right? So between two tensor core operations, there's no tensor core is free, so it's not fully taken. The utilization isn't that high, but with ping pong, the bubble is almost gone. It's very minimized, and the softmax operation here overlaps really good with the tensor core operations, and this gives better throughput in general. Yeah, so with all those techniques, we can push up the distributed attention kernel to almost double performance. And the same set of techniques also apply to regular attention on Hopper, and this gives a pretty good speed up too. And the same kernel, the regular flash attention kernel on B200 actually benefits additionally from some other techniques, fine-tuning techniques, but we are also able to manage to get very good performance out of it. So looking ahead, we are extending TLX in two major directions, exposing more hardware features and new platform support. For NVIDIA GPUs, especially for the Blackwell hardware, we are adding paired CTA and cluster launch control, and also distributed shared memory support. These help push the coordination between CTAs more tighter. And yeah, we'll briefly talking about paired CTA and CLC later. And on the AMD GPU path, we are also trying to support users with the same interface. But some of the features are not available on the hardware, like for example, the wave specialization support. Hardware do not have very supportive barrier natively, and we are actually implementing it on the software side. But yeah, so we are getting there by giving users exactly the same interface on both hardwares. So yeah, let's take a look at the paired CTA mode, how it works exactly. But before we get there, let's briefly review how single CTA works here. So with single CTA mode, you would have many CTAs running its own tiles, right? They are independent, they do not work with each other. And each CTA will start loading a full tile for A, M by K, and K by N, and compute the M by N tile. And two CTAs is gonna compute 2 by M by N tile, of course, right? So it works like loading data and do MA and release the buffer in an iterative way. And with two CTA, in TLX, they don't differ too much, right? Two CTA modes, one CTA can still compute M by N tile, and two CTA still compute 2 by M by N tile. But what's different here is the B tile is shared across CTAs. So one CTA only owns half of the B, and half of B is still stored in one CTA and they store in another CTA. So they co-load the same B and share with each other. And this reduces memory traffic literally. And also it reduces shared memory usage, as each CTA can only need to allocate half of the B size, right? And the additional change, actual change here is just one pair of barrier and wait, because B is shared across two CTAs. CTA 0 needs to wait for CTA 1 to complete before moving forward. And also the MA op here is kind of broadcast MA, so one CTA issues MA for both, but the MA itself can update the barriers on the both CTA sides. And we actually see a pretty good speed up with this. So it's generally 2% over single CTA, and now with TLX warp specialization, we are getting almost 98% of the Q+ Gen performance. This is on Hopper. The feature is only available on Blackwell. Yeah, and we are also bringing up the support cluster launch control, CLC support. So this is particularly useful for imbalanced workloads. And it's different from the traditional like static tiling stuff. You would have a gem kernel runs under a persistent K loop, and each CTA gets a fixed amount of tiles to handle. And this works pretty dynamically. And as this diagram shows, it works in 2 steps. In the first step, each CTA starts its own assigned tile, and it could finish later or sooner. It depends on the computation of the tile. And then once it's finished, it tries to cancel a yet launched CTA and grab the work from there and do the work for it and cancel that CTA. So at runtime, there's still going to be a persistent amount of CTAs created. And each CTA works in an iterative way, trying to do its job and cancel the other CTA and do the other work. And yeah, so this is pretty dynamic, but still in a persistent way that all SMs will be very busy. So to wrap up, TLX stands for Triton Low-Level Language Extension. And it offers hardware control within the Trident ecosystem. And it's available through the Meta's open source repo. Actually, this is the production branch we use internally. And we provide good spec and barrier manuals and a lot of tutorials for you to get up easier. And it currently supports NVIDIA GPU on Hopper and Blackwell, and AMD GPU support is coming. So yeah, try it out and let us know what you think. Yeah, that's all. Thanks for listening. Yeah, question time.
Thank you very much. And can you comment on how TLX can be effective on other accelerators, MTIA?
That's a very good question. We haven't started yet another unlike GPU platform, but I think it's possible as long as your hardware has some intrinsics you think user can use to control its performance, it should be exposable through our interface. And in general, the register schematics inherits from what Trident compiler does exist for now, and we are only adding memory schematics on top of it. So if your hardware supports, local memory hierarchy, then this will be a good place for you. Yeah.
Hello.
Hi.
I was looking at that too simplicial attention blog post, and in it I noticed it says that the Trident compiler backend couldn't perform the necessary pattern matching and skipped optimization, and you guys encountered compilation errors for warp specialization. It wasn't clear to me that as Trident improves, if you were to implement these kernels in 5 years, let's say, would these TLX features become obsolete, or is there a reason to think that Trident will always work at a certain level of abstraction, in which case, why not Gluon or something like that? Or were there informed assumptions that were made that the compiler couldn't?
Yeah, that's a very good point. We have tried a similar effort by reducing users' effort of manually specializing their work partition. And I think the abstraction can go further. And basically, user can specify a little bit directives to the compiler or writing the programs in that way, and the compiler can do a better job there. It also depends on how the hardware converge. If the different GPU platforms diverge too much, it's going to be hard. But yeah, in general, I think fully automatic compiler optimization is possible. It just takes time, and we need to study many patterns before we converge on a really solid model there.
So is the goal sort of for TLX to die eventually?
I hope so. I hope programmer will have a better, easier job.
Great.
Whatever, yeah.
Thank you.
No problem.
Hi. So you mentioned that you can manually allocate shared memory tensors, right, or tiles.
Yeah.
Does that mean you can also dynamically index into those tiles?
Definitely, yes. So the pipeline index is dynamic, right? So which buffer you are referencing depends on the current tile ID, loop indexes. That's already variant. Yeah. But the number of buffers must be static, because this is stack allocation on the CPU side, because they only have a fixed size of shared memory.
Thank you.
Yeah.
Okay. My question is, since this morning have the introduction on Helium, right?
Helium, yeah.
Helium, yeah, right. Since it's the upper layer on top of the Triton, right? And the TLX actually is the lower level language extension. So which one will have a longer life cycle, or to say that have a better optimization for the hardware performance?
Yeah, I think Helium in general gives a bigger, broader roadmap for future development. So if hardware are going to converge their design, then Helium will be a better choice for users. So you write a kernel once, it runs everywhere, right? But for now, hardware diverges a lot. And TLX is just a practical way for you to get there, to unblock yourself immediately. And compiler work is coming in. but it still takes time. So if you don't want to wait, you can just unblock yourself using TLX. It's something temporary, but I think it also depends on how hardware evolves. So yeah, if hardware becomes very complex and especially regarding async programming, then it will be out of control. Then we'll think about how to support portability there.
And yeah, so if that's since Helium is also by the Meta team, right? So
yeah.
in your strategy, I want to know, will you combine the Helium and this TLX together to give a better performance in future? I don't know. What is your strategy?
That's a very good question. Yes, we are doing both. We are prioritizing both. As I said, TLX is a more realistic way to unblock performance for now, but Helium is on the way. So we are also actively working on compiler support, trying to get everything we can in a more reliable way. But yeah, it takes time. So this thing will coexist for a amount of time.
I see, yeah. And my last question actually is, sorry, I don't know if you heard about the Thailand.
Thailand, yeah.
Yeah, because DeepSeek, they use that. So it's based on the TVM and also have a lot of hardware specialization, design, extension, right? So have you compared the performance of the Thailand for some typical implementation versus the TLX?
Yeah.
How you compare?
To be honest, we haven't. So we've been working hard on getting TLX kernel up to date. So we are achieving really good performance there. I think fundamentally they don't differ too much from each other, but it's all rely on the backend compiler's quality. I think with Triton we are keep improving it, and it's NVIDIA PTX compiler is sometimes it's also we need to consider. So it's all about downstream toolchain, but on the upstream we are exposing everything we can. I think eventually we will be giving you the exact same performance. It's all up to programmer how to program there.
Okay, thank you.
Thanks.